Yeah, thank you.
Yeah. So your LiDAR sensors are basically laser lights. They're very powerful. They're very expensive, but they're very accurate as well. So they also can work really well in like foggy conditions, rainy conditions, and even precipitation like snow. But they cannot process images and color properly. So this becomes a problem, right? So if you're having a self-driving car and it is just fitted with a LiDAR sensor, it will not be able to tell whether the traffic light is red, yellow, or green. So that's a problem. But despite the fact that it can, you know, properly detect people, properly detect obstacles. So you also have your camera sensor. Your camera sensor might not work well in, rain or in snow, but they can detect images. They can detect color. So they'll be able to tell you, okay, the traffic light is red. So this is a very important point. Uh, you cannot rely on just one sensor, all right? You need to rely on multiple sensors. Uh, and sometimes these sensors are complementary. So you can see right here, what the LiDAR sensor fails at, the camera sensor sort of excels in. So I'll sort of get to this point again in the future because there is a way to combine these separate pieces of information in real life robots. Okay, so now with proximity sensors, you can basically tell what are all the different objects that lie in like the vicinity of your robot, but it doesn't tell you the complete picture. Your robot is still sort of blind. So your localization sensors sort of give you a more complete picture of your overall environment. More specifically, your localization sensors will tell you, okay, I am currently in this location right now. So there are basically three types of localization sensors. One is your odometry. So you have your car's odometer, right? So they basically tell you, I've traveled that. Using that information, it can sort of like integrate the distance traveled. Sorry, it can sort of position of the robot, but it's not a very robust analysis. So that is why you need to rely on other sensors. For example, your GPS. So everyone's pretty much heard of of your GPS, right? It can basically tell you where you are in the world, but your GPS might not work in sort of like if you're going through a tunnel or something like that, or if you're operating a UAV, right? If you're doing some search and rescue operation, you're inside a burning building or something. Your GPS will not be able to tell you, okay, where it is. So you'll need to rely on your odometers to fill in that information. The last type of localization sensor is your IMU. So this is very popular in UAVs. And so IMUs are basically the last type of localization sensor. They are very popularly used in UAVs and in aircraft. So if you attended my last lesson, aircraft was right, and I basically said that it was I think Aditya was the one who mentioned that your UAV is a 6-degree freedom of robot. Yeah. So you basically have your X, Y, and Z coordinates, and you have your roll, pitch, and yaw. So your IMU is the sensor that gives that information. You all must have experience using an IMU yourselves. So whenever you enable that tilt option and it tilts your screen or something, yeah. So that is basically like your gyroscope, and your gyroscope is like a part of your inertial measurement unit. Yeah. So
I have a question there.
yep.
So how does IMU combine the inputs from all the three sensors and make it one? Like how the process happens?
Oh, okay. I am not too acquainted with that. So yeah, these are all these are all, I wouldn't necessarily call them different sensors. Sometimes you can get a single sensor that just gives you acceleration information. Uh, but yeah, I'm not too familiar with the science behind getting these individual pieces of information. Uh, you just have to know that IMUs are the type of sensors that give you that information. Yep.
Does IMU come preloaded with accelerometer, gyroscope, and magnetometer, or you have to get a separate component and attach an IMU to your robot?
Yeah, that's a good question. So in the market, you can see different types of IMUs. So there are there are two types. They're basically a 6 DOF IMU and a 9 DOF IMU. So a 6 DOF IMU will give you 6 pieces of information: AX, AY, AZ, and your row pitch yaw. With AX is your acceleration in your X direction. Whereas your 9 DOF IMU, right, it'll also consist of your magnetic heading. So it'll contain information on your magnetic north, stuff like that. Yeah, there are basically three pieces of information there as well. So a 9 DOF IMU will contain the six separate pieces of information from your gyroscope and the three magnetic heading components.
Thank you.
And these are quite cheap also. I don't know how much they cost in India, but they might cost like 500 rupees. But another thing is these things are extremely noisy. So this is another point that I will bring up in the next two slides. Yeah. So these are some of the other sensors. So for example, your Mars rover, right? Your Mars rover won't just have your localization and proximity sensors. They'll have a bunch of other sensors, like your pressure sensors and whatnot. But for the sake of simplifying your study in robotics, you can technically ignore them for now. But just note that there are other sensors out there. Okay, so now that we know what sensors are commonly used in robotics, there are two pieces of information that you need to know when you're actually using sensors in real life projects. One of which is a software which I would want some of you guys to use, especially if you guys are undergrads. The other is an algorithm, which I'll get to. The first thing is called a software called Robotic Operating System, or ROS. So in the field of robotics, many things are reusable. So if you buy a Roomba, right? Roomba might be a bad example, but yeah, let's say you have an open source Roomba. You purchase an open source Roomba. You will not probably write your own obstacle avoidance code or your own path planning code. Many of these things already exist. People have done work on them. So ROS, one of the functions that ROS provides is like a uniform, standardized way of, having these algorithms downloaded onto your actual hardware. And another thing that ROS does is that it sort of standardizes the whole data acquisition process. So suppose you're working with a new IMU, right, that you just purchased, and you don't know how, like one of you mentioned, you don't know how the physics works behind getting your acceleration or your magnetic heading. So ROS provides a standard way of retrieving this information so that you don't have to write that messy code that works with that sensor's hardware. You can just plug your ROS module, and it'll automatically get your data in a neat package. So it's essentially like an IoT platform that communicates with your software's hardware, and you can basically manipulate the data directly itself. So for those of you who are undergrads, or those of you who have Linux machines, I strongly recommend that you guys follow the tutorials and download ROS here. And keep in mind that this is not just used in robotics. Whenever you're working with cameras for machine learning purposes, you'll find that ROS is quite handy. It's quite a handy tool. So yeah, and if you guys have questions, you can always reach out on how to get stuff working on ROS, because it's kind of like a messy headache. At least I find that. The second point that I want to bring to your attention is, something that I've sort of alluded to throughout the course of this lesson, and that is that we cannot just rely on one sensor. So you've seen examples that the LiDAR sensor cannot work with, detecting color or detecting images, and your camera sensor cannot work in the presence of heavy precipitation. Another thing to note is that all sensors have noise in them. So what do I mean by noise? Uh, so think of noise as like a constant error. So when we so when we people have like an eye defect, right? When we have like short sight or something, uh, the sight that we see is not like the perfect sight. There are always some discrepancies, so that's why we wear glasses, right? At least some of us do. So you can think of like uh, this particular algorithm as like a corrective measure to whatever your sensor ends up reading. So suppose your ultrasonic sensor is detecting like an object that is 5 meters away, right? But you know that the sensor is kind of noisy. Your Kalman filter, which is the algorithm that basically does all this cleaning up process, is the algorithm that sort of removes out all the errors and gives you like a closer estimate to what the truth is. But it's important to note that you will never know the truth in science or in robotics in particular. You'll only have like a better estimation of the truth. So your Kalman filter is an algorithm that does two things. One is that it combines information from different sources. It can combine sensor information from your camera and your LiDAR sensor to give like a composite data package. Another thing that it does is it tries to remove all the errors to some extent. So a small picture might help you out right here. So these are some of the sensors that are used in a self-driving car in action. So you can see that this is a long-range radar. It is used to detect images that are, obstacles that are very far away. Then you have like a short or medium-range radar, which detects objects not so far away. So what would happen if like a person were to come in between those the ranges? So it cannot entirely rely on the the long range radar, but it cannot also rely entirely on the short range radar. So it has to sort of combine the information from those two sensors to give like a best estimate of, the blind spot, so to speak. So this process is called sensor fusion. Um, I'll also share this PPT with you guys, and I'll also give a small link to how Kalman filters work, because frankly speaking, this is something that you would learn during your master's program. But I just wanted to, if you ever decide to do something in robotics, but I just wanted to give give you guys a heads up, and whoever wants to sort of get their hands dirty with them, uh, you can reach out to me and I can give you sort of assignments on that. Okay, so that's basically the theoretical aspects of today's lesson. Are there any questions? Oh, another thing is, this is a very powerful algorithm. It is not just used in robotics. So believe it or not, people have also used Kalman filters in determining stock prices of companies. So something that might not seem that relevant, it finds a use in. So basically anything that you want to, anything that has uncertainty in it, right? You can sort of use a Kalman filter to some extent to, weed out the uncertainty. I've also attached a link to, using Kalman filters and predicting stock prices for those interested. But yeah, just another thing. Okay, so any questions so far? If not, I'll proceed with the demo and VREP.